Welcome or welcome back, for those of you who have joined previous talks as well, to the 7th edition of Programmers Week. Like we promised, this year we go beyond with great tech talks spread across 6 days, split by domain of interest. And we are now in the 5th day, which is focused on AI, big data, and analytics. I'm Victor Lupaescu, Community Manager for DevOps and Big Data at Cognizant Softvision, and I will be your moderator for the next talk. So let me introduce you to our next speakers, Ioan Sighiartau and Ovidiu Oprica. They are two DB engineers passionate about winter sports and SQL Server. And since winter is not here yet, they only have SQL Server left. Closing to 10 years in Cognizant Softvision and working together on the same projects for more than 7 years, they always had in common the curiosity of understanding how the SQL Server engine works. They figured that Programmers Week 2021 would be a great place to share some of their knowledge and experience on this subject. So in the next 45 minutes, they'll open SQL Server's hood and talk about execution plans. But before passing them the mic, I encourage you to share your questions in the chat module, and we'll address them at the end of the session. Ovidiu, Sigi, you have the mic.
Thank you, Victor, for the kind introduction. Let me share my screen real fast. Okay, thank you for the kind introduction. Let we as well welcome everyone to our presentation. My name is Sighiartau Ioan, and together with my colleague, Ovidiu, we will go over SQL Server under the hood execution plans. On today's agenda, we have a few bullet points. We will go over why execution plans are important, what happens when a query is submitted, general rules on reading execution plans, and then we will go over most frequently used operator. In the end, as Victor mentioned, we will go over the Q&As. Without further ado, let's get started and explain why execution plans are important. Let me put you into perspective. Having nice things is great. For example, owning a great car. Who doesn't love that, right? Remember the Need for Speed days? But as everything great in life, things eventually break or they start performing poorly. What happens then? What do you do? Well, you might say, Sigi, that's pretty simple. I will just hire a mechanic. But what if you can't afford one? I know it's stupid to assume you have a great car, but you cannot afford a mechanic, but let's just go with the flow over here. You have to pop up the hood and take a look and see what's happening inside in order to fix the problem. Let me ask you, would you do it yourself? In a similar fashion, when SQL queries start performing poorly, we need to pop up the hood and take a look at what's happening over there. And we can do that via execution plan. So in a scenario where the client complains that the app has started performing poorly, worse and worse by the day, and the volume of data has increased, of course they are not going to hire an external DBA to do your job, right? So everything boils down to, do you as an engineer understand execution plans? If yes, then the answer is simple. Sure, we'll get back up to speed during the sprint. If not, the only reply you can have is something like, oh man, that's really unlucky. Try deleting some data. No one wants to hear that, let's be honest. Okay. Moving forward, to better understand what's happening under the hood, let's take a look at what happens when a query is submitted. Whenever we press the F5 button and we execute a query, everything goes to the relational engine. This is the main actor. And we have two phases, the compilation phase and the execution phase. Inside each phase, there are processes that do important work for us. For example, we have the query parser. This is the process that will make sure that the syntax is all okay. For example, if you have written select instead of select or form instead of from, it will just give an error and the story will end up there. But if everything is okay, you have been careful with your spelling and you introduce commands that are recognized by SQL Server, a parse tree is gonna be passed to the next process, which is the algebraizer. The role of the algebraizer is to bind the objects. Basically, it takes the query, takes a look at all the objects that have been referenced, table, columns, indexes, whatever you have placed there, and it makes sure that these objects exist. An exception to this rule might be when you create a store procedure. It will just check to see if the store procedure can be created, and it will not take a look inside of the store procedure. And this is actually smart because this allows us a little bit of flexibility to reference maybe some temp tables that have not been created yet, but we are sure they will be created at runtime. Once the algebraizer is convinced that everything is okay and that we have referenced only objects that exist, it will pass a query processor tree to the next process, which is the optimizer. And this is an important one, especially for our talk today. Think of the optimizer as your friend that translates from Spanish to English when you are in Spain. Basically, what the optimizer does is it takes the query that you sent and all the logic that it has there and tries to translate it into physical operations. It will try to find out operators to read the data, to join it, to do computations and stuff like that. And it will try to do that several times. It will try different combination of obtaining the same data that you have requested. And it does that for a few times, as I just mentioned, based on the estimates that he has. The optimizer will estimate how many rows are in the tables, and once it is pretty sure that he has found a good enough solution, because this will not go on forever, it has just a limited amount of time to find a good enough plan. When he found a good enough plan, it will pass it to the execution engine. And this is where the next phase starts. The execution engine will pick up the execution plan that have been created by the optimizer and follow the instructions just as they have been sent to it. So we can say that the execution plan is literally a set of instructions on how to execute a query. Or how I like to say it, execution plans are a window into SQL Server soul. But let's pause for a bit and take a step back. Did I just say that the optimizer uses estimates to create the plan? Further, let's take a look at the importance of statistics and do a little bit of role play. We are here, the query parser, check the syntax, everything is okay. Algebraizer, verify the objects, they are all okay, gives the green light. Then the optimizer starts. We are here. Basically, the optimizer will say, I'm going to estimate how many rows are involved in this, and based on my estimates, I'm going to create a plan on how to get the data. You say, could you not estimate? But the optimizer replies, do you want me to read the whole data from all the tables in this query? At this point, usually you don't have a comeback. And in the end, optimizer usually replaces with an arrogant line like, that's what I thought. So the optimizer will choose the lowest cost plan based on an estimated cost. And that is fine because we don't want the optimizer to read all the data from all the tables referenced in the query each time it tries to generate a plan. Instead, the optimizer relies on statistics, which are aggregated information based on a sample of the data and in some cases based on the whole data. And that information is used to generate the plan. Statistics usually have information about the cardinality of the data, selectivity of the data. They contain a histogram. And all of this is important because these are the estimates that the SQL Server engine, the optimizer, actually uses in order to create the plan. So I cannot stress enough how important it is to have a statistics maintenance process in place so that the estimates are accurate, so that the plan that is generated by the optimizer is as accurate as possible. By default, statistics are being updated when more than 20% of the data has been modified, or when we query a table and we filter on a column that doesn't have statistics, or when we create a new index, that's when the statistics are being created. So we talked about statistics and the importance of them, how the optimizer generates an execution plan. But what happens then? Let's take a closer look. The optimizer, if it receives a simple query, it can generate the execution plan sub-second, just like that. But in some cases, when the queries are more complex, the optimizer takes a little bit longer, minutes or even more. So it's important to store that execution plan once it has been created. And SQL Server will store it in a section of the memory called the plan cache. And it will try to reuse that plan wherever it is possible to reduce the overhead. Basically, once the algebraizer gives the green light for the optimizer, together with the query processor tree, it will pass a hash value for the query text that have been submitted. And the first thing that the optimizer does is it takes a look and see if for that hash value, do we have execution plan already stored in the memory? If yes, it will pass that execution plan to the execution engine, and we can bypass the whole operations that the optimizer has to do. This is actually pretty smart. We would like to store all the plans in the memory and keep them forever there. But in a real life scenario, let's be serious, we cannot do that. Memory is expensive. So each plan has an associated age value that is computed using the estimated CPU cost of compiling the plan and multiply it by how many times it has been used recently. That's how we come up with the age of the execution plan. And that is pretty smart because we want to keep up in the memory longer the plans that are harder to compile or that have been used frequently. Then the lazy writer process, which is an internal process that works to free all types of cache, periodically scans the objects and then decreases the value each time it goes by. When a new query is submitted in the plan cache, and if the plan cache is full, it will flush the oldest plans and make room for the new ones. But enough with the talk. I know you want to see how we can get an actual execution plan. And we will do just that. We will take a look at general rules on reading an execution plan. And we will do that via demonstration. For the purpose of this demonstration, I have picked the Stack Overflow database that contains data from 2008 up until 2013. Oh, wow, I forgot to delete this. Oh, sorry, this is so embarrassing. Okay, just pretend you didn't see that. Let's say that we have a simple query. We want to get all the data for the user with the display name Siggy that has created some posts between in the time frame of October 2008 and November 2008. And we want to have that data order descending by creation date. We can obtain the execution plan of this query multiple ways. We can press this button that says include actual execution plan or Ctrl-M in the keyboard. Or if we just want to see the execution plan without running the query, we can display the estimated execution plan. I know, online there is all this fuss about differences between the estimated execution plan, the actual execution plan, how they are different things, how the engine somehow changes the plan at runtime and changes its mind. None of that is real, guys. Basically, the estimated execution plan is the same as the actual execution plan. The only difference is that the actual execution plan will contain runtime information, so you can compare the estimates via the actual stuff that happened at runtime. For the purpose of this example, let's generate the actual execution plan. We are executing this query, waiting a little bit to get the results. It shouldn't take long, and there they are. We received all the data that we asked for. In the messages tab, we can see how many records have been affected by our query. And then we have the third tab that will show us the graphical execution plan. You might panic at this moment. Oh my God, what are all those little squares and arrows and text in green that tell us to do something? Chill out, guys. It's not that hard. I basically train my cat to do this. So just wait and we'll show you how to do it, no worries. How should we read an execution plan? We take a look. The recommended approach would be to read the execution plan from right to left, top to bottom. Of course, in some cases, it might make more sense to read it from left to right, but that's a more advanced technique, so let's stick with the basic for now. You can see different operators shown here in the execution plan, and basically each operator does something. Some operators will read data, some will join data, some will do different compilations or sorting or stuff like that. But we will take a look at the most commonly used operators in just a bit, so don't worry about that one. Besides this, you can see the data flow arrows. That will tell you the direction from which the data is flowing and how many records are being passed from one operator to the other one. Basically, if an arrow is really thin, it means that few rows have been passed to the other operator. If an arrow is thick, then it means that a lot of rows have been passed to the next operator. You can hover over the arrow and it will show information on how many rows have been passed. Besides this, a worthy thing to observe is the operator cost. This will tell you, relative to the query that has been executed, which operator had a higher cost or a lower cost. In our case, the keylookup operator had a cost of 86%. The index scan, 13%. Another thing that you could observe is the cost, the query cost relative to the whole batch. In this case, is 100% because we only had one select statement in the batch. But for example, if we were to have 3 select statements, then each select statement will give you the query cost relative to the batch. Of course, you noticed the green text telling you that you are missing an index, and SQL Server will show you this. And it's worthy to take a look, but please don't create indexes like crazy whenever SQL Server tells you to create one. I know it says here it will increase, they have an impact of 1000% and it will make your life a whole lot better. Don't trust it. Take a look, see if you're actually missing an index, see if you're gonna get some benefits out of it, and if yes, then create it. By right-clicking on any of the operators or by hovering over them, it will display different important information. For example, if we select the select operator, pun intended, we can see different properties of the execution plan, like the cache plan size, how much memory has been granted, the optimization level, and all the other good stuff. You might as well have observed that this operator has a little yellow warning sign. It means that at runtime something happened. In this case, SQL Server had to make an implicit conversion from a typing mismatch. It had to make a conversion from varchar to nvarchar. In some cases, it will tell you that the memory grant was excessive or that it's built to disk or stuff like that. So it's worth taking a look. Now that we have an idea on how to read an execution plan and what's happening over here, I will pass the mic to my colleague Ovidiu to tell you all about the most frequently used operators.
Thank you, Siggy. Now let's look into this. So while SQL Server has a lot of operators, we're only going to be covering the most frequently used in order to make this presentation easy to digest. Also, because after our presentation, our manager has his presentation, and running late with this to cover all of them would be what scientists commonly refer to as a career limiting move. So let's get into them. The first operator, the first set of operators that we'll be covering are data reading operators. No matter what you do, you'll end up using these because you will need to read data from a table if you're actually using a database. Now, on first look, it might seem like this is a lot of information to take in, but all of these are can be basically grouped into three categories: a scan, a seek, or a lookup. And how these work is if SQL Server needs to do a scan, let's say for the sake of example that we have 100 records. If you're forced to do a scan, then SQL Server will read all 100 records, even though it's only returning one. This is because you don't have an index to help you identify your specific record. A seek, on the other hand, will only read the records that are needed. In this case, you only read one out of that 100 in order to return your one. You can think of it as the number of the pages. Since in an index, the data is ordered, you wouldn't need to randomly shuffle pages looking for page 45. You're going to know where to find it because it's going to be between page 44 and page 46, unless there was a printing mistake. Now, a lookup is a combination of a seek and a scan, so to say, for one record. It reads the records as a seek, but then it also needs to go to the table outside of reading the index in order to, to return the columns that are not covered by the index. So for our 100 records, it does a single read, but twice in order to return that one record. And let's have a look on a practical look. So from the Stack Overflow database, if we want to bring in all of the users that have a specific create date, well, we can see in this case, we have a scan because there's no index on the creation date as suggested by SQL Server that we're missing it. We can see that we do a scan, and this is because the column is not ordered, so it wouldn't know where to stop or where to start. What happens if we do include the suggested index? We add it to the table. You can see in this case that this turned into a seek. Now the data being ordered as the ordered property suggests, either by hovering or by opening the properties. You can see that it's ordered. It knows exactly where it needs to locate the specific record. Now on to a different example based on location. So we have the index, it does a seek. What happens if we also want to show the display name? Well, in this case, we're getting a key lookup. And if we look at the output list, we can see that the display name is being brought in as a key lookup. Well, the cost of the lookup is 74% of the total cost. So it's pretty costly to do a key lookup. How does this change for a larger data set? In this case, we had one user. What happens if we get 170,000 users. How is this going to change? Well, in this case, SQL Server decided that rather than do so many individual key lookups, it's better to just do a scan. It's going to be faster. So on the surface, it might seem like the scan is the weakest, lookup is better, and the seek is the best. The scan and the lookup can be interchangeable depending on how many records you're trying to read. Also, it might seem like the conclusion of the first part of the operators is that everything should be a seek. You turn every select into a seek, an index seek, and problem solved, or all your queries are incredibly fast, no problem. Well, there's a cost to it. You pay either on waiting for selects or on waiting for inserts, because every index needs to be updated as well. Let's see what happens if on the comments table we've added these 6 indexes, and now we're trying to insert a new record. How does the execution plan handle this situation? Well, if we look at the object, we can see that in addition to the primary key, to the clustered index, it's also updating the additional 6 non-clustered indexes that we've added. In this case, it's irrelevant since we have a 0-second runtime, so it's not going to matter. However, in real life situations, when you're inserting 1 million records, this will get costly very quickly. So you should use them sparingly. On to the next one, the data joining operators. What do these do? So whenever you have data that is stored across multiple tables that you need to unify as a single result set, you will need to use a join. Between 2 tables, there's no way to do a freeway join all at once. And whenever you do a join, one of these operators will come into play. The nested loops work best when one of the tables has a small data set. If we look over to the operator, how it looks in the execution plan, it gives us an indication of what it's going to try to do. If we consider that the join tables are A and B, well, A should have a small number of records because it's going to do a search. So for each element in table A, which we can consider the blue arrow, it's going to search for all of the records in table B. So if table A has 10,000 records, then it's going to search table B 10,000 times to get all of the matching records. As you can imagine, this is not ideal for performance. And this is why SQL Server will only use it if one of the tables is small. Now, on to the next 2, the hash join and the merge join. These work in a similar fashion with one difference. For the merge join, the data needs to be sorted, and it needs to be sorted on the join condition. So if the data is sorted on user ID in the users table, but we're actually joining to creation date or location, then we won't be able to properly make use of a merge join. And that's where the hash join helps us, because it's able to do the join even if there's no way to get the data pre-ordered. And the last one, the adaptive join. It's a combination of a nested loop and a hash match, which will be chosen at runtime based on which one is going to be a better performer. However, an adaptive join needs SQL Server 2017 or newer. It needs a column store index on the table. The query needs to be run in batch mode. It needs to be a Friday the 13th. It needs to be sunny outside. So there are a lot of conditions to fulfill in order to be able to make use of it. So you might see it less than the others by a bit, just a bit. Now, let's see how this performs in practice. If we're trying to bring in the users and their posts by joining the users table to the posts table, how is SQL Server going to handle this? As you can see, in this case, even though the arrow is thicker and it has a higher number of records on the second table, since the first table is small, it chose to do a nested loop because it was the faster option. What happens if we have a larger data set? Well, in this case, we get a hash match. This is because even though the users table does have an index, as you can see, the data is brought in by an index seek and the order property is true. In the case of the post table, the owner user ID is not ordered, which means we can't properly leverage the merge join. Now, SQL Server does offer us an option. We can force a merge join. However, you really shouldn't do this. You're more likely to break something than fix something. And as you can see, we do get the merge join, but this is still an index scan. The data is not sorted. So in this case, SQL Server throws in an additional sort operator in order to get the data sorted for the merge join operator. And you might think that 6% of the total cost isn't all that bad. We might consider throwing in a merge join every now and then. What happens if the number of data coming in changes? We've added an additional 0, so we went from 10,000 to 100,000. And the sort cost increased from 6% to 21%. And this will only get higher as more data are brought into the operator. So this is not the way. What if we add the index that was suggested by SQL Server in order to have the owner user ID sorted? How is this going to affect our query or execution plan? Let's never mind. In this case, both of the reading operators are 6, and the data is now ordered in both cases. So now we have a merge join the proper way this time. So while the hash join is a weaker version, so to say, of a merge join, if you are able to, you should try to add the indexes, but only if it's really worth it. Try to find the sweet spot between having everything indexed and only merge joins and making use of what's making use of the hash joins. Now, on to the next one, the data aggregating operators. And first off, we're going to start with the sort operator. What it does, the sort operator takes the data that it receives from the previous operator, it sorts it and returns the same data in an ordered fashion to the next operator. One thing to keep in mind is that this can be a bottleneck because all of this is performed in TempDB, and this is used by all of the databases. So even though we're using our Stack Overflow 2010 database, if we had 3 additional databases, all of them would create a bottleneck in TempDB, one for the other. And also, you might be wondering, looking at your execution plan, why is there a sort? I'm not doing an ordered by. I didn't type that in my query. Why do I see a sort in my execution plan? Well, as we saw previously, when we forced the merge join, it's possible for SQL Server to realize that it needs the data ordered and throw in one on its own. As we also saw earlier, one way to get rid of the order by is to add an index. If you already bring in the data ordered via the index, there's no need for additional sorting. So that's the cleanest way and easiest way sometimes to remove a sort operator. Also, it's possible that you're doing multiple order bys in the same query when you only need to sort the data at the end. These are sorts that can be removed. There's no additional benefit unless you actually need the data sorted for your calculation. And let's see, let's see some sorting on the users table. Well, if we order the data by ID, we can see that there's no sort operator because the index scan brings in the data already sorted. We are getting the first 100 users directly from the clustered index, so no additional sorting is needed. However, if we want to sort by an additional column, by a different column that isn't included in any of the indexes, this time we will get a sort, as there's no way for SQL Server to know what are the most reputable, actually the least reputable users. Now, on to the next ones. The stream aggregate and the hash match aggregate. What these do is if you want to see, let's say you have a table with temperatures by day, and you want to see what was the average temperature for December of last year to get a feel of what might be coming this year. Well, this is the thing that you type in SQL Server is going to be a group by, and one of these two is going to work in the execution plan. The data needs to be sorted in order for this to work, because SQL Server needs to be able to group all of the data into December in order to make a group. So if the data is already ordered via an index, the index needs to be on the columns that we're grouping by. This is similar to the join, and also similar to the join, the stream aggregate will work if we do have that index, while the hash match will work regardless. It doesn't need the data to be sorted ahead of time. Let's see this with a practical example. So if you want to see how many posts each user has, in this case, the object being read is ix post owner user ID. The data is ordered, and we will have a stream aggregate. What happens if we lose the index? In this case, we're going to get a hash match. For the same outcome. Next, we have the spool operator. Well, this isn't directly tied to aggregation. It is used by aggregation when, depending on the calculation, we need to reuse the data multiple times in the same execution plan. And we have two types of spool, the eager spool and the lazy spool. The difference between them is that the eager spool is a blocking operator, while the lazy spool is a non-blocking operator. What that means is that the lazy spool will read one line and pass it on to the next operator. It reads line 2, it passes on and so forth. While the eager spool needs to read all of the data before starting to churn out anything at all. Similarly, a sort operator is also a blocking operator because it's not able to read one line, sort it, and pass it on. Read the second line, sort it, and pass it on. That wouldn't make any sense. Initially, we only had the lazy spool. When I say initially, I mean 40 years ago. And this can cause problems. The reason the eager spool was created was because if you're reading a range of values, so to say, and you're updating incrementally, like reading salaries, if you're reading all of the salaries that are below a threshold and incrementing them by 10%, what happens if you're using a non-blocking operator is that you're reading line 1, you're updating it, and you think you're passing it on to the next operator, but you're actually passing it, depending on the amount added, you're able to pass it on to your first operator and then reread it again, and so on and so forth. And you're basically updating all of the records up to that threshold. And this isn't an imaginary scenario. This actually happened, or so legend says, a while ago. Now, let's do a quick recap of what we've discussed in the lesson. We went over why execution plans are important, what happens when we submit a query, general rules on reading execution plans, and some of the most frequently used operators. Now, if there are any questions, also we have a QR code on screen for the feedback form for this presentation.
Thank you, Ovidiu. Thank you, Sigi. Really awesome presentation. And you stayed in time, so your job seems to be safe. So let's
Thank
see
God.
on the on the question side. We do have one question, and that is: does the hash join work on non-equality condition on the joined columns?
The hash join requires at least one predicate to be equality, because it will use the equality predicates to create the hash key. And then on the hash bucket scan, it will evaluate the other non-equality conditions that it has.
Okay, thanks for the answer, Sigi. It seems we don't have any further questions. We'll soon close this this session, but we're continuing with with the big data topics and data in general. I'll be next as a presenter. So if you really want to talk data to me, see you in 15 minutes.
Thank you, guys.
Thank you.